Hello everybody. Today I'm going to go ahead and show you guys how you do electron configuration models. I know you've already learned it in class, but just wanted to review this with you. So why do we use the electron configuration model? Well, we can't use a Bohr model anymore because not everything moves in a spherical motion. Electrons don't move in just that way all the time. They move in other shapes as well. So if you take a look here, we've got spherical, dumbbell, and then we have like a shorter dumbbell shape. So as a result, the method that we use for electron configuration is a little bit more symbolic than what it has been before, and appears to sometimes be confusing, but it really is not. So let me go ahead and show you how to do that. So the way that I typically teach my students to do it, and there's two different ways you can do it. One, you can use a periodic table, and one, you can use a chart. And the chart that I use is created from the periodic table. So if you look at a periodic table, there are 7 periods. 1, 2, 3, 4, 5, 6, 7. So let's go ahead and just number them on here. And you can break the periodic table up into 4 sections. The first section up here is S. The section over here is P. The section in the middle is D. And the section in the bottom is F. Now, if you notice that the atomic numbers go from 57 to 72, that's because these, Glenn Seaborg was actually the scientist that said these don't really belong in the top of the periodic table or in the middle of the periodic table because these guys are radioactive. So he yanked them all out. Okay, so actually 6 and 7 still continues down here. So I'm going to use that information, those periods. I'm going to create a chart. I'm going to go 1, 2, 3, 4, 5, 6, 7. And then I'm going to stagger it, and I'm going to start at 2 and go 3, 4, 5, 6, 7. And then I'm going to go 3, 4, 5, 6, 7. And then 4, 5, 6, 7. And I'm going to put these new shapes that these electrons can move in there as well. So everything in the first column is going to get an S. Next column is going to get a P. Next column is going to get a D. And the last column is going to get an F. Just like that. And then we're going to draw diagonal arrows going through like this, which symbolizes the direction that we're going to go with this model. You're always going to start up here, and then you're going to basically go through each of these. These are called sublevels. I like to tell my students they really represent shapes, where S represents a spherical shape. P is the large dumbbell. The D represents the short dumbbell. And then the F, the shape can vary. And the letters actually represent, you can have a certain amount of electrons that fit into each of these into these different sublevels, into these shapes. So in the spherical, you can hold up to 2 electrons. In the P, you can hold up to 6. In the D, you can hold up to 10. And the F, you can hold up to 14 electrons. Okay, so really what I've done is I've taken the periodic table that's here, and you can see here's your S, that's my first column, and then we have P, that represents this column, and then we have D, and then we have F, which are the ones down here at the bottom. Okay, so it's created from the periodic table. Okay, so how do you do this? So we're going to go ahead and take an element. We're going to take, like, for example, the element calcium. So you put the abbreviation for calcium there, and then you want to look on your periodic table. Calcium has an atomic number of 20. So in the isotope form, that would mean that the bottom number is 20. And then if you round this to 40, that would end up being your top number. And so really what this front half of the electron configuration does is it gives you the number of protons and it gives you the number of neutrons in the atom. That's important to include that information. Right? So the number of protons here is 20. And then if we do the math and we subtract these, because this is the total number of stuff that's in the nucleus, if we subtract them, that will give us the 20 neutrons that calcium has. Now, since there's no charge on this, this is not an ion, and it's neutral. That means that if we have 20 protons, that means we also have 20 electrons. So that's the number that we're going to go to. So we just follow our electron configuration. We go through 1s first, and then we take a look. S can hold up to 2 electrons. So we put a little superscript of 2. And what that means is you have 2 electrons in the first energy level moving in a spherical type pattern. Okay? Kind of like the Bohr model. I mean, so right now this is really just, the Bohr model could represent this information too. But as soon as you get past the S's and you start using P's like dumbbells, then that's why we have to use the electron configuration model, because you can't really just draw a dumbbell over top of the Bohr model. It doesn't work. It'll get really complex and confusing if you were to overlap all those shapes over top of each other. All right, so the next thing we go through is 2s, which is 2. And then we go through 2p. Now we have to be careful because p can hold up to a maximum of 6 electrons. And then after 2p, we go to 3s, and s can hold up to 2. And after 3s, we go to 3p, and p can hold up to 6. So let's see where we're at so far. So far we have 2, 2, and 6, which gives us 10, 11, 12. Yeah, we can go ahead and fit 6 more there. That will give us a total of 18. And then after we get through 3p, we go to 4s. And then 4s would end at 2. And that's all you need. And you can stop on this last one. It doesn't have to have 2. It can have up to the max. So, let's say this was a D and it was a 10. You don't have to actually put 10 there. You can put like maybe 3 in there or 4 in there, however many you would need, so that when you add up these superscript numbers, you get to your total of 20 down here for calcium. Okay, so that's a standard electron configuration model. Now, when you do electron spin, what you do is electron spin shows that in an orbit, you can have up to 2 electrons max. So what does that mean? That means that in this sublevel, in this shape that the electrons are moving, these 2 electrons, because there's only 2 of them, there's only going to be 1 orbit. So we're going to represent the orbit with a box. In fact, anywhere we show an S, because the rule is 2 electrons can fit in an orbit, and then because S only holds 2, that means there can only go 1 orbit. We're going to put a box everywhere we basically see an S. Now for P, P6, 6 electrons are in there. So how many orbits would that have? Well, 2 divided into 6 will give you 3. So we're going to go ahead and draw 3 boxes here wherever we see a P. And so how many would you have for D? Yeah, you'd have 5, because 10 electrons can go into a D. Well, 2 divided into 10 gives you 5. All right. Now the electrons, according to quantum theory, if one of them is rotating one way around the atom or spinning in one direction around the atom, the other one's going to spin in the opposite direction, and they repel each other. And every once in a while they hit each other and get knocked into a higher energy level and get excited, and then they come back down and they emit that energy as a form of light. Okay. But anyway, so we're going to go ahead and put 1 electron in that first box, and then we're going to go ahead and put another electron in the other box, again showing them and going in opposite directions in each of these boxes. Now it's important when you get to 3 orbits in a sublevel, each one of these orbits is pulling on the electrons with the same amount of force. Okay, we're pulling on the electrons with the same amount of force. Well, why is that? Okay, so if we take a look at, this is what I started with. This is the P. Okay, there's actually, if you look at this, there are 3 dumbbell shapes over top of each other. Each one of those can hold up to 2 electrons, and if you look at them, they each extend the same distance away from the nucleus. So that means it requires the same amount of energy for those electrons to be in each one of those orbits within that sublevel. Okay, so we have to evenly distribute them like this first, because each orbit's pulling on that electron, trying to attract it with the same amount of force, and then you're going to go ahead and you fill it in like that. Okay. And then we'll do the same thing for the S. We'll put an arrow in there, and then a down arrow in there, and then for the P, we'll go up, 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 and then we'll go ahead and go down, down, down. Now this would be important, because if this was the last one, this was a 4, let's say it was 3p to the 4th, and you were to go ahead and fill it in, then you would want to go 1, 2, 3, evenly distribute the electrons first, because each one requires the same amount of energy to be there, so you want to evenly distribute it, and that's harder to put the second electron in. So when you're done, then go ahead and start over by pairing them up. Okay, kind of like when you do a Lewis dot diagram, you go around it. Okay, you just put one on each side, and then you start to pair it up. All right, so same kind of idea. And then since this is 2, it's an up arrow and a down arrow. If this was a 1, you just have an up arrow, and that would be it. So that's electron spin. Okay, and there is a shorter way to do it, and that's called the noble gas core configuration. All right, so right now we just did the electron configuration. And then with the bottom part, we did the electron spin. And then the next part that you can do is the noble gas core configuration. So how the heck do you do the noble gas core configuration? So let's do the same element. You got calcium, 40 over 20 Ca. Okay. What you're going to do there is the same idea. You want to go ahead and go through all the way up to 20, but you don't have to start all the way from the top of the chart. Okay. What you can do is you can start at the nearest but smallest noble gas. So when you do noble gas core configuration, you pick the nearest but smallest noble gas. Okay, well, what the heck does that mean? All right, so let's go back to our periodic table. Okay, so if we take a look at where calcium is located, which is right here at 20, if we go to the nearest but smallest, well, it's at 20. So we're going to look way over here, and the nearest but smallest would be argon. Okay, right here. Wouldn't be krypton, that would be the larger one. We want the nearest but smallest. Okay, both these are near, but argon is the smallest. So what does that mean? That means that you're going to put AR in brackets, and you see how it goes up to 18? So you're going to put AR in brackets after it, and then you're going to go ahead and stick an 18 in. Now, not everybody does this, but I think it's really good because it allows you to keep track of the electrons and how far you've gone so far. So what you've done is you've already done 2, 3, 4, 10, 12. You already did all the way up to this point right here, 3p6. So all you have to really do is add this 4s2 on there, and then you're finished. So you just put your 4s2, and that would be your noble gas core configuration. You've got 18 plus 2, which gives you your 20. All right. Now, remember, I said there's another way to do this. Okay, this is a way that I teach my students how to do it, but sometimes you can, other teachers will use like the periodic table to do it, and you can do it the same exact way. Okay? So let's take a look at our original periodic table that we kind of already marked up here. So notice that we got 1 through 7 for our periods. They represent that first large number when you write down something, okay, which is this one, which represents the energy level. We should probably label these here. So this represents the energy level. And then if you look at this number here at the top, this represents the superscript. It represents the number of electrons. And then the letter represents what we call the sublevel, or I just simply call the shape. It's the shape that the electrons are moving in. So how this reads is, in the first energy level, 2 are moving spherically. In the second energy level, you have 2 moving spherically, but you also have 6 moving in a dumbbell shape. Okay. Third energy level, you have 2 moving spherically. In the third energy level, you also have 6 moving dumbbell. And then it actually has a fourth energy level, but 2 of them are moving spherically. So you can see, because of these other weird shapes, you can't use the Bohr model anymore. We have to use this electron configuration model, which, is what we use since now of quantum theory, okay? Which is a lot of what this information is about. Okay, so let's go back to the other way to do it. So if you take a look at the original periodic table, let's say we're going to do calcium, this guy right here. Okay. So what you would do is to say, okay, well, notice that helium can really kind of fit all the way over here in that other box. It makes sense to actually put it there. But the reason, and in some people will argue that it belongs there because, go 1, you go 2. This element has 1 electron, this has 2, just like these guys have two electrons in their valence as well. But helium is stable with 2 electrons in its valence. And so actually that's why it fits over here in the noble gases. So you can actually move this really kind of all over here. And so what we're going to do is we're going to say 1s, and then helium would be so this would be 1s1, and then helium would be 1s2. And then we are done with elements in this row, so then we come over here, and now we're at 2s. This area is s. Remember, I separated it right here. And then we're going through both of those elements, so that would be 2s2. Notice that's what we have in our model. We have 1s2, 2s2. And after we finish these elements, now we go over and go through 5 through 10. Well, that's in the p area, and it's separated right here. So that would be 2, and then this is the p, and we're going to go through all these elements, which would be all 6 of them. And then we come over here, and we're going to go through 3, and then s, and we go through both of those, so that would be 2. So there we go, 2p6, 3s2. And then after that, we move over here, we're going to go through 13 through 18. What's that going to be? 3p6. Yep, 3p, and we're going to go through all 6 of them. And then look, now we're over here, and we only have 2 elements to go through. And that would be 4, and then s, and then 2. And then you would stop. So you can use the periodic table to do it. The problem is when you get to elements like this, let's say you had to do iron, okay? It would have the same electron configuration as calcium. It would go all the way up to 4s2. But then you might say, okay, well, that's pretty easy to do. I'm going to just say 4d and go 1, 2, 3, 4, 5, 6. There's an exception. When you're doing this group here for the d, you want to take the period, whatever it might be, and you want to subtract 1 from it. So actually, it's not going to be 4d, 1, 2, 3, 4, 5, 6. It's going to be 3d6, okay? And you can kind of see that in our model because, of what we did here. Because after you go through 4s, what do you come to next? You go to 3d. It's like the number goes backwards. You don't go to 4d, you actually go to 3d, okay? Same thing for down here, for F. If you were to do anything down in F, which I usually don't give my students any numbers that go all the way down that far, but you would take the period and you would minus 2 for those. Okay. So that's it. So I hope that was valuable. That's basically how you do electron configurations and also electron spin and also the noble gas core configuration. All right. Thank you very much.